Today we're going to be continuing our unit on stoichiometry, and that means that we are going to be again using our mole-to-mole ratios, but also including mole island from last semester to do some conversions and predict reactants and products. So basically today we are going to be using both the mole-to-mole ratios and mole island like I just said. But for our mole-to-mole ratios, the important part is that we are using them when we are converting from one substance to another, right? So if I am going from iron to oxygen in this equation, right, in this balanced equation right here, I have to use my mole-to-mole ratio of 4 to 3 in order to predict or calculate anything. So every single time, just like with at the end of last unit, how we had to use our mole-to-mole ratio to predict the number of, let's say, moles of iron in iron 3 oxide, you had to go to moles and use your mole-to-mole ratio to jump from one island to another before we could do anything else, really. So, remember, going from one substance to another, we're always going to use that mole-to-mole ratio. Now, we're also going to be using the rest of our mole island conversions in order to figure out how many, what our mass might be or what the volume might be of a reactant or product also. So our first example, actually, you should write this down right here. Example 1 includes the same balanced equation that we worked with last time. So 4 moles of iron react with 3 moles of oxygen gas to produce 2 moles of iron 3 oxide. How many grams of oxygen are needed to react with 5.42 moles of iron? Last time we figured out how many moles of oxygen would be required. This time we're going to just take it one step further and figure out how many grams of oxygen that actually is. So the first thing I do, start with my given. The next thing I do is I use my mole-to-mole ratio, right? So I'm going from moles of iron to a new mole island for moles of oxygen. Then when I'm in my mole island for oxygen, I'm going to be able to predict how many grams of oxygen that is. So then I go ahead and cancel these guys out, plug in 4 moles and 3 moles, and then for every 1 mole of oxygen gas, I end up with 32.00 grams of oxygen gas.
Nope. Cross out the moles, not grams.
Oh, sorry. Right here. My bad. And my answer is 130.08 grams of oxygen gas.
And then we're going to round it for sig figs. So we're going to round for sig figs, take it down to 100 and...
I had 3 sig figs, so it's going to be... Yeah. It's going to be 130 grams of oxygen gas. I need that decimal there because that 0 is significant because I started out with 3 significant figures here.
All right, so let's take a look at another problem. This is going to take it even one step further. So just now we started in moles and went to grams of another substance. Now we're going to start in grams and go to grams. So if I have 100 grams, if 100 grams of CH4 reacts with excess oxygen, how many grams of water vapor would be produced? So I'm starting with...
Excess oxygen, by the way, just means that we have as much oxygen as we would ever need. And that's important when we actually get to our next learning target. So,
yeah, so ignore that. Just know that it's enough to make the reaction happen, okay? So we're going from 100 grams of CH4 to grams of water vapor, all right? So if we're using this mole-to-mole island, right, we're starting in mass. So we have mass. We have to get to moles of CH4. Once we're in moles of CH4, we go to moles of H2O.
Using our mole-to-mole ratio.
Right, and then once we're in moles of H2O, we can go back down to grams. So that's 1, 2, 3 steps that we're going to need. So 1, 2, 3. If you want to set it up like that, you know you have 3 steps coming. All right, so the first thing is I have grams of CH4.
Is that balanced?
Oh, thank you. We have to make sure that we're using a balanced equation, right? Because our moles are going to be all out of whack if not, right? So CH4, we have 4 H's. We need 4 H's over here. That now gives me 4 O's, so I'm going to need 4 O's. Okay, now we have a balanced equation. and I can come over here, and I have grams of CH4 that needs to go on bottom because I have grams of CH4 on top. On top, you know, we always do 1 mole. So 1 mole of CH4, we need the molar mass of CH4. The molar mass of CH4 is 16.05 grams, okay? And my grams is gone. Now I'm in moles of CH4. I have to get into moles of water vapor. This is going to be my mole to mole ratio, and I actually put this right here for you. This step right here is that new step that we're adding in, the mole to mole ratio. So I know I'm going to have mole over mole. On bottom, I have to have mole of CH4 because I have mole of CH4 on top here. So the mole of CH4 has to go down here. That means on top, it's going to be mole of water vapor. And we look at our balance equation. I have 1 mole of CH4, and I have 2 moles of water vapor. All right, once I have all of this, my moles of CH4 is gone. Now I'm here, I want to get down to mass. So we're going to have to put mole of water vapor on bottom, and on top, grams of water vapor. Okay, we're using our equivalency statement again. There's 1 mole, and how many grams of water vapor in 1 mole? 18.02 grams of water vapor. Moles of water vapor crosses off. Okay. Now we're going to multiply across the top. We're going to divide across the bottom, and we end up with 224.5 grams of H2O. And we want to check for sig figs. We have 4, 4, and 4 sig figs. So our final answer has 4 sig figs, 224.5 grams of water vapor.
So if I started with 100 grams of methane and that reacted with oxygen, we would end up with that much water vapor at the end. That's what we just found out. Okay.
One more example. This time, instead of going grams to grams, we're going to throw in a few more complications, all right? You guys have done the equivalency factors using moles and particles and liters, all right? So we're going to actually incorporate that into this problem, okay?
You're writing.
I'm writing.
Okay, so we're using the same already balanced equation. So again, methane reacting with with oxygen is going to create carbon dioxide and water. Remember, that is a combustion reaction. So if we start out with 5.00 times 10 to the 24th molecules of methane, and that's reacting again with excess oxygen, how many liters of carbon dioxide gas at STP would be produced? So I am trying to get from particles of methane to all the way to liters, volume, yeah.
Not liters.
Of particles to volume, yeah. Volume of carbon dioxide, CO2. So along the way, I am starting at particles of methane. I have to go first to moles of methane. Then I can go from moles of methane to moles of carbon dioxide. Then from moles of carbon dioxide to volume of carbon dioxide. So this is a 1, 2, 3-step problem. Great. So I'm going to moles, and then to moles of methane, to moles of carbon dioxide, and then moles of carbon dioxide to my volume of carbon dioxide. Okay, so 5.00 times 10 to the 24th molecules are of methane on the bottom, and I'm trying to get to moles, so over 1 mole of methane on top. So for every 1 mole of methane, I have 6.02 times 10 to the 23rd particles, or molecules. So I go ahead and my molecules cancel out. Then I can use my mole to mole ratio to hop from one mole island to the next. So for my moles of methane are going to go on the bottom, and my moles of carbon dioxide are going to go on top. This is where I can't just use like 1-to-1 or whatever anymore. I have to go back to my original balance. This is our new step. So for every 1 mole of methane, I have 1 mole of carbon dioxide. Sorry, it's 1-to-1. That's okay. Right? You have to go back and make sure. So 1 mole of methane for every 1 mole of carbon dioxide. Now that I am in moles of carbon dioxide, I can go ahead and figure out what my volume of carbon dioxide would be. So for every 1 mole of carbon dioxide, I actually have 22.4 liters of carbon dioxide. Remember? Now, volume, we're only going to use that when we're talking about a gas at STP. Now, for this unit, you can assume that we are at STP.
And I put STP.
That's what we're going to include, but don't freak out if we forget to put that in one of the problems, right? So for right now, we're assuming we're at STP, but we couldn't, well, for this problem, everything's a gas. But sometimes we're going to end up with, like, aqueous solutions or something that's a solid, and you're not going to be able to predict. We don't have an equivalency statement to figure out the volume for that. So we have our 22.4 liters on top. We're going to cancel out our moles of carbon dioxide. We are in our liters of carbon dioxide, which is our volume, which is what we wanted. Multiply across the top, 5.00 times 10 to the 24th. Remember to use your EE button. I would really try this in your calculator right now because we still need practice. Times 22.4 equals, divided by 6.02 times 10 to the 23rd. Also don't forget your parentheses, equals 186 liters of carbon dioxide, 3 sig figs, 3 sig figs. Because that's what our given was. And there you go. So if we started out with this many 5.00 times 10 to the 24th molecules of methane, we are going to end up producing 186 liters of carbon dioxide. That's a lot of carbon dioxide.
All right.
That's it.
That's all.